Hi, welcome to this video, and in this video I would like to talk with you about the question how a particle accelerates in a fluid. And therefore we make a short repetition of the terminal settling velocity, because so far we already discussed quite intense how particles settle, and therefore we need a very short repetition of what we know already. And then you learn what changes if we consider the particle acceleration in their motion, because this is something we neglected so far. Terminal settling velocity means there is no acceleration, and now you learn what happens if we look at the acceleration. And finally, we will also solve the general equation of motion. So we will set up the general equation of motion, and we will solve it to calculate the time needed till a particle reaches a terminal velocity. Because there is a certain time the particle needs to accelerate, and then the particle stops acceleration and has a final terminal velocity. And we will use the equation to calculate this time. So this will be a rather theoretical video, but I think in the concept of particle motion it's also important to look a little bit more detailed into the theory. So if we start with a short repetition, maybe you remember this video, or if not, this is a brine, a lithium brine, and this is used to evaporate water and to enrich lithium for the lithium mining, right? And this is something we took as an example because the lithium is in the liquid is precipitated, and then we get lithium particles, and these lithium particles are settled down in such a sedimentation tank. So you see here these lithium carbonate particles, which are precipitated, sorry, they are precipitated out of the brine, form particles, and these particles settle down. So the velocity of the particle was important here, and this is the terminal settling velocity, and this terminal settling velocity for one lithium carbonate particle was calculated by a force balance, and the force balance was the gravity, the buoyancy, and the drag force. And then we can, so the drag force in Stokes regime, so very slow settling, laminar flow, and then we can make the force balance rearranged to the terminal velocity, and then we get the stationary terminal settling velocity. And this is something you should already know from the previous videos. And now we would like to take a little bit more detail into the case that we have also the particle starts accelerating before it reaches this final velocity, right? And therefore we have again take a look at the force balance. So we still keep one dimension, right? Because settling can easily seen as a one-dimension problem. And if we take a look at the force balance now, we have the gravity, we have the buoyancy, we have the drag force, and now we have one force which is new, and this includes the acceleration, and this is the inertia, right? The inertia has the acceleration, and what happens is we have our lithium particle, and the lithium particle at time zero has a velocity zero. And when it has a velocity zero, the gravity is pulling it down, and the buoyancy works against the gravity, but since the density of the particle is larger than the density of the fluid, the gravity is larger than the buoyancy. So we have something left over here if we balance the force, because this arrow is much longer than this one, and the particle starts to accelerate. And against this acceleration we have the inertia, right? So the inertia acts against the acceleration. And if we now start the time running, so t is larger than 0, the velocity increases because the particle accelerated. And with increasing velocity, we get now resistance from the fluid. So we get a drag force. And the drag force acts against the motion and decreases or slows down the acceleration. And when the acceleration slows down, the inertia slows down, right? So here's no movement, no velocity, and this means we have maximum inertia and no drag, and then the particle starts to move, the velocity increases, the drag increases as a resistance against the velocity through the fluid, and with this the inertia decreases because the acceleration decreases. And if we wait a little bit more longer, time is even increasing. And what happens is that we reach a final constant velocity. And this final constant velocity is the terminal velocity you saw on the previous slide and know from the previous videos. And this is a constant velocity, right? And this means we don't have any acceleration anymore. And this means inertia is completely gone and the drag force completely replaces the inertia from the beginning. So here we have now reached steady state terminal velocity. So if we take a look at these four forces, basically this is what you know from the videos before, right? So there's gravity, buoyancy, and drag and Stokes regime. And now we get a fourth force new, and this is the inertial force, and this is F equals ma. And if we put this in the same typo as here, so we have the density of the particle, this is a spherical particle, and here we have the acceleration, and the acceleration is the change of velocity divided by the change of time, so dv divided by dt. And now we put all of these four equations in the force balance you saw before, and this looks more complicated than it is. You just take gravity, buoyancy, drag force, and inertia, and you have to consider the directions, right? So this works down, the others work up. And now we can rearrange a little bit, and if we rearrange the equation, so plus this, minus this, minus this, and then we can take out the brackets, take them out of the brackets, and then we have density particle minus density fluid, and here we have the same term here and here, and this is minus 3 pi dp viscosity velocity. Okay, and now we can rearrange a little bit further. So we divide by the density of the particle, we divide by pi, we multiply with 6, and we divide by d to the power 3, and then we will get the final differential equation, and this is dv divided by dt, and now the pi goes away, the particle diameter goes away, the 6 goes away, from the 3 we get an 18, the pi goes away, right, and the density goes here, the velocity stays, the viscosity stays, and this goes down here to the power 2. And this is the important equation, right? So this is the final differential equation describing the settling of a particle considering acceleration. So it starts from 0, it accelerates till a final velocity, and this is in this equation. And this equation has the solution, which you see here, okay? So if you want to solve this differential equation, this will be the solution. And if you look a little bit closer at this solution, you see that the first part here looks very familiar, or should look very familiar. And this is the terminal velocity in the Stokes regime. So this is what we calculated for the settling of one particle, right? And this makes sense, because if this goes to 1, so there is no acceleration anymore, this is the leftover, and if there is no acceleration, this should be the terminal velocity. And then we have 1 minus e to the power minus t. T is the variable, t changes 1 second, 2 seconds, 3 seconds, and now we have a t star. And the question is, what is t star? And t star is basically the vice versa from this expression here, so density of the particle times diameter square divided by 18 of and viscosity. And why t star? Because if you look at the units, that's density and that's length squared. So density, length squared, and here we have dynamic viscosity, Pascal seconds. And if you just work with the units, Pascal seconds, and this is done, then you have kilogram meter seconds, this cancels out, this cancelled out, and we have seconds. So this is a time. And this is a characteristic time, and it simplifies the equation because we don't have this big guy here, we just have the t star. So what is t star? And now we can take the equation, we simplify it a little bit. So this is the Vt, so this is the expression here, right? We put the Vt in here, and we make t equals t star. So when we say t star equals t, this expression goes 1. And if this expression goes 1, since it's an exponential function to the power minus 1, and we have minus 1, so this means this whole expression here is 0.632 if this expression is -1. So this means t star is the time till a particle reaches 63.2% of its stationary velocity. And this is a very well-known value for exponential functions or for e functions, right? And if you think a little bit further, this is what I meant before. If this whole part goes to 1, this one goes to 1, and then the velocity is just the terminal velocity. So there is no acceleration, and the equation from before for the terminal velocity is the same as we get here, even if we consider acceleration. But after the time the acceleration is done, just Vt is over. So what you also can do is you can say the particle displacement after time t can be calculated by integration. So if this is the velocity and you integrate the velocity over time, you will get the distance. So you can calculate the velocity of the particle, and in the same way you can calculate which distance the particle goes in a given time. And this is basically the integral of this equation. So the Vt, and then we have t minus t star, and here it's the same because it's an e function. So a very simple expression. Once you know t as a variable, t star normally is known if you look in density, viscosity, so that's quite easy. The settling velocity also can be calculated. So here we have two expressions to calculate the velocity and distance of a particle accelerating. However, basically that's already is, but when I was a student, I was always a little bit unhappy because normally you get, when you look into the books, you find the force balance, you find the differential equation, and you find the solution. But what I would like to show you is how you get the solution, how to solve the differential equation. If you're not interested in this, you can skip the video here and directly jump to the end. But if you like to see how we solve the differential equation, which is, I think, a good task for engineers, then just stay with me and then we take a look. And what we have to do is we take the differential equation. So this equation here is the equation we have here. Yeah, so that's the equation, the final differential equation. And we have to rearrange it a little bit into a solvable general form, because differential equations, it's like cooking. Okay, so you have a certain differential equation and there are recipes you can use to solve them. And therefore you have to rearrange them a little bit. And what you see here is what we call an inhomogeneous ordinary first order equation. And this can be solved by a very straightforward way. So here we have dv dt, here we have a term with the variable v, and here we have a term without v, so no dependency of v. And what we can do, because it's still a quite big equation, we can simplify it a little bit, because all of this is constant, so we call it a, and all of this is constant, so we call it b, and then we have a very simple but general equation, dv divided by dt plus av equals b. And this is, as I mentioned, the inhomogeneous ordinary first order equation which we have to solve. So first we make a homogeneous equation out of it, and this has to be solved. And this means we have to solve to v, the velocity, which is depending on the time, right? But we change the equation a little bit, so now it equals 0. This is called homogeneous equation, and therefore we get the indice velocity h, velocity homogeneous. So the first we have to do, now it's quite straightforward, separation of variables v and t, right? We have the variable v, we have the variable t, so we separate them, so minus av, and then we get this expression, and then we divide by v, we multiply by dt, and then we get this one, so dv divided by v. So now the v variable is here, the t variable is here. And if we want to solve it now, we have to integrate it. So we take the equation, we integrate the equation, and this is 1 divided by x, or 1 divided by v in this time, and the integral of 1 divided by x is ln x, and so 1 divided by v is ln v. And here we don't have any variables, so the integral is a constant, and for this part, which we can take out of the integral because it's a constant, we get now a variable. So we have a minus at plus constant 1. And if we want further solve it towards v, we have to take the e function. So now we have v, and since it's homogeneous equation, right, it's equal 0, we give it a specific indice. So it's the velocity for the homogeneous equation as a function of t, and now we have e minus at plus c1, and then we can rewrite this expression here, and this is e to the power minus at multiplied e to the power c1. And since this is constant, right, e is a fixed number, c1 is a constant, I can give it a new name, and this is c2, and that's easier to write. So I have a new constant here. This one stays as it is, and this is the solution of the homogeneous equation. So the first part is already done. Then we take a look for the second step, and the second step is searching for a specific solution. And the specific solution now means we want to have again a solution of the equation, and we want to know what is the velocity, but in a specific solution, so it gets the indice sp for specific. And in the specific solution we say, okay, b is a constant, so we assume that the velocity is a constant too. And if so it's not depending on t anymore, and if this is a constant, this goes 0, and we have a constant value here, right? So VSP, and if you compare to here it's depending on t. Now it's a constant, not depending on t anymore. And this means we have a, we have b, and we know what is a and b, right? Because a and b was a constant we defined a few minutes ago, so we can rearrange this expression to v specific equals b divided by a, and then we put what is b, we put what is a in there, and then we do a little bit the math, and we will get this as a leftover, and this leftover is already known for us because this is the terminal velocity in the Stokes regime, meaning the specific solution of this equation when we say the velocity is constant is the terminal velocity, which completely makes sense, right? Because this is what we assumed all the time before. Velocity is constant, then we use this equation. So we can say the specific solution is the terminal velocity. So now we need to find a general solution of the equation, and the general solution of the inhomogeneous equation is the sum of the homogeneous solution, so the first solution we have, and the specific solution, so the second solution we have. So we need velocity homogeneous as a function of t, right, acceleration in here, and specific solution where we said vt, terminal velocity. So this means we can say the general solution vt equals, this is the what we want to know, right? dv divided by dt has to be solved, so we want to have v as a function of t equals. And this is the homogeneous solution plus the terminal velocity. And now we can, inside the homogeneous solution, which is constant 2, multiplied by the e function to the power minus at. So now we need to determine the constant ct2, right? Because we don't know this, the rest we already know. And therefore we look at the initial condition. And the initial condition says that the particle at time t0 has no velocity, right? And this is what we assumed already in the schematic I showed you, where the particle has no velocity and the gravity pulls it down, so it starts to accelerate. And if this is the case, we can say at t0 the velocity is 0. And if we put this in here, t0 velocity is 0, so here is a 0, right? Velocity is 0, t is 0, so this expression goes to 1, this stays, and this goes to 0. So if we say now minus this expression, we will get c2 equals minus v terminal velocity, right? Because this term will be 1, so this can be just go away. So c2 plus v2 equals 0 means c2 equals minus vt. So now we put c2 equals minus vt, not vs, vt, into the general solution obtained before. And then we can write vt equals minus vt multiplied e to the power minus at plus vt. And this is the same as we just switch the positions, right? Vt mean minus vt multiplied e to the power minus at. And then we take it out of the brackets, and then we get this expression here, right? So the v goes out of there. And then we know what is a, and this means we put the a in here. And now it should be look very familiar to what we saw before, because now we can define a characteristic time t star, which is this expression, and then we will get, if we define it in the vice versa, we will get the equation vt equals, so v as a function of time equals the terminal velocity multiplied by 1 minus e function to the power minus t as a variable divided by characteristic time t star. So that's the same equation as I showed you before, and this is how we can solve the differential equation. You just can work with the equation and the solution, or as I showed here, you go step by step and solve the solution, the equation by yourself, which I think it's worth to do to get a little bit more the understanding. And now we can plot this, and if we plot this, and this is for a lithium particle of 1 millimeter in water, which is quite a large one, but just because the numbers look nice. And what you see here is the velocity of the particle. You see the acceleration, and then you see that at one point this is the terminal velocity, and you see how it reaches the terminal velocity, and it reaches the terminal velocity quite fast, within half a second. So this means if we generally look at settling, assuming stationary settling is basically a good assumption, because even for smaller particles, this terminal velocity will be reached much faster. So it's a good assumption, but you see how the acceleration behaves. It's as an e function. And therefore I have some tasks at the end for you to train your knowledge. And the first one is that you recap by yourself and set up the force balance on your own, right? Think what happens during the acceleration, how the force balance changed, and just set the force balance for your own. Write the forces in there, and then try to solve the differential equation by your own. The recipe is here in this video. And then as a third task, calculate the time and the distance needed to reach from velocity 0 at time 0. So that's the starting velocity, 99% of the terminal velocity. So what is the time I need for a particle, lithium particle of 20 micron, till this particle reaches 99% of its terminal velocity, and what is the distance this particle travels, and calculate this in water and in air. It's not completely perfect, the task. There are some some things are not perfectly correct, but it's a nice task to try. And it's very common to use these 99%, because when you go by theory, you never reach the 100% due to the function, right? So 99% of the terminal velocity is very common as a defined number to reach it, and then compare what happens if you do this in water and in air. So with this, I would like to repeat the video. So I made a very short repetition of the terminal settling velocity on the example of lithium, right? What's the force balance, how we calculate this. And then we learned, or I showed you what changes if we now consider the acceleration of the particle and the motion. What changes in the force balance, and how this force balance changes over time. And then we have a final equation of motion, the general equation of motion, and we have a differential equation for this, and therefore we solved this equation, and we took a look for one specific case, what is the time needed till a particle reaches its terminal velocity, which is below 1 second, so therefore terminal velocity is generally a good assumption. Therefore, I would like to thank you for watching the video, and if you have any questions, just let me know.